Go. Okay, so let's have a look. There we go. Let's go here. File, open. And let's go up here. And go up again. There we go. We'll be able to do this. Maybe. Okay, there we go. So as I mentioned, this is kind of the start of a series of engineering classes that you're going to take. So let's first point something out. I mean, imagine you've taken Engineering 112 or some equivalent of that. But other than that, you've taken probably a lot of math and science courses. So one thing I want to mention is this is engineering. We have applied practical problem solving versus a somewhat more theoretical approach of math and pure science, okay? So that's something we'll touch on as we go through the class, but I just want to point that out to you. We're in a little bit different world here in engineering, okay? Like if I'm designing a bridge, I don't so much care if I totally theoretically understand the bridge so much as I care that it stands up, okay? So my focus is a little different than it is in science or math. So I approach things differently, okay? So just be aware of that. Some of the things, a lot of what you learn in math and science translates right into here, but we do things a little differently sometimes, okay? So what we want to do in this class is we want to learn about mechanics. We want to learn and practice analytical problem solving, because that's what engineering is often all about. And we want to learn to present our work that's organized and can be followed. Okay, so let's have a look here. First thing I want to talk about is significant figures. And what I want to tell you is the significant figure rules. Use 3. Okay, we're done. Okay, got it? I'm building a bridge. I don't care about significant figures that much. Doesn't make any difference to me. 3 figures is fine. I usually I keep the numbers in my calculator if I need to. If I have to start carrying things over, I carry 4, I report 3. Good to go, okay? All right, now a few things here. In math, you're taught to present answers. Oops. Remember the right screen to use here, I'll be able to talk about this. In math, you're taught to do things like give answers like 4 pi and things like that. Like the one thing that comes to my mind is all the trigonometry, like the sine and cosine of, I'm gonna, I think, shut that door, I think. Okay, so like in math, they have those different values for sine and cosine, right? As you work your way around the circle there, like pi over 3 and all that kind of stuff. Don't tell a machinist to cut a piece of steel pi over 3 inches long. Don't even think about doing that, okay? So I don't want to see an answer like that. I can't do anything with it, okay? Now it's fine for math, and math is good stuff. We need to use that. We need to learn it and apply it, but we're applying it now, maybe a little differently than how you learned it. So if, I don't tell somebody to lay out a line that's 4 pi feet long either, right? Nor do I tell them that. Can a machinist cut a piece of steel that long in inches?
Depends on their budget.
There you go. Yeah, they could probably do it. But what's going to happen to the cost of that piece of steel when you start telling them to do that? It's going to go way up, yeah, because they're going to have to precision measure it. Okay, so 3 figures, 12.6, good enough, okay? For what we're doing, it's fine, okay? So I want to get that across. I don't like seeing answers like this. This is not, if you're giving me an answer like this, you're not quite on board with engineering just yet, okay? You're still thinking kind of more theoretically, okay? You all good with that, what I'm saying there, okay? So keep that one in mind. Okay, now we're going to look at the effects of forces on objects. Objects at rest is statics. That's what we're doing now. A lot of you will take dynamics next term, perhaps. That's objects in motion. Actually, you can get a little bit more technical about that. Dynamics is often accelerating objects. Statics is objects that aren't accelerating. A little bit more formally, you could state it like that. Okay, now we do use, a lot of physics and mathematics when we analyze stuff. So let's look a little bit at that. Mass is the amount of atomic material. It's a resistance to a change in velocity, okay? So mass is how much stuff there is in something, how many neutrons and protons and all that stuff in there, okay? That's mass. A force is a push or a pull. So a weight is the force caused by gravity. So mass is measured in kilograms in the metric system, and there's an odd unit in the English system that's called a slug. Okay, those are the units of mass. The units of force are newtons in the metric system and pounds in the English system. Okay. Now in this country, I think I mentioned, we use the English system quite a lot here. We've tried to go over to the metric system or international system as it's called sometimes, but we haven't done that yet. We're one of the few countries in the world that still uses the English system. England no longer uses it. Okay. Did I mention this? The other 2 countries in the world that use the English system? I can't remember. Liberia, that's right. And another economic powerhouse in the world, Burma, Liberia, and us. Okay, those are the 3 countries that are still in the English system. We keep trying to make a run at the metric system, but we just never seem to quite get there. Okay. Now we can relate force and mass by the amount with which gravity causes an object to accelerate when it's in Earth's gravitational field. That's typically referred to as G. So in the metric and English systems, there's G, 9.81 meters per second squared, 32.2 feet per second squared. So the basic relationship here that's used is F equals ma. The force is equal to the mass times the acceleration. Weight is equal to mg. So on Earth, there's a pretty consistent relationship between mass and weight. If you start taking things up to the moon or something, it's not so consistent anymore because G will change in different locations in space. But if you're doing your engineering here on Earth, it's a pretty constant relationship. Varies a little bit depending on elevation, but not enough that I would ever be so concerned with it, okay? All right, so the basic relationship that we use, primarily in this class that we use, is weight is equal to mass times gravity. So 1 Newton is 1 kilogram meter per second squared. 1 pound is 1 slug times foot per second squared. Okay. All right, now here's another thing I want to mention. Bring those notes to class with you all the time once you buy them. I'll just run through this stuff because I've got it written down for you, okay? If you're copying all this stuff, it's just hard to write it all down, So I just write it down for you, okay? All right, so we good with that? Okay, all right, we're good with that. All right. Now let's look, and I don't think I wrote this one down, so let's find a space vehicle has a mass of 135.2 slugs. That's English system mass. Let's find a few things. Its weight in pounds. Its weight in newtons, because those are the English and SI systems. Its mass in kilograms, its mass on the moon, and its weight on the moon. And what I give you there is conversions. The pound is 4.448 newtons, and the moon's gravity is 5.325 feet per second squared. just roll that ahead for a second. Okay. So this is just going to be an exercise in converting things, is what this is going to be. And also in using the F equals ma formula, or its corollary, W equals mg. Okay? All right, so we're good with that. All right, so what we have here are the basic relationships that F equals ma, and the corollary to that is W equals mg. Okay, so G is 32.2 feet per second squared, and that's 9.81 meters per second squared. So to get the weight, I would take the mass times gravity. Now, when you do that, be sure you're using the proper gravity. I've seen people do this incorrectly a number of times. I've got a mass in slugs. That's the English system. So I want to use gravity in feet per second squared. So if I do that and I run the numbers, I get about 4,350 pounds. Okay. And then I can convert that to newtons pretty quickly too. And notice I'm carrying my units through. I'm being a little careful here. Okay. What I'm trying to do is save some time. I'm trying not to make mistakes. So I carry stuff through and be sure I'm laying it out and making sure the units cancel and all that good stuff. Okay. So when I do the units on there, I get slug foot per second squared, which is equivalent to a pound. And then I can convert that into newtons. Okay, so we're good with that? So we get the weight figured out by taking mass times acceleration, and then we convert that into newtons. We're good? All right, now I can run that formula backwards and divide gravity out. And that will get me the mass. Okay, so if I take the weight in newtons, the 19,364, and I divide it by the metric system gravity, I'll get the number of kilograms, 1974.
Force on the moon.
Yeah, I'm just finding mass right now. What's that? Yeah, it is important to keep them straight. That's why I'm going through all this, just to kind of emphasize that. Now that's on Earth. okay? But the mass doesn't change. So you're gonna have the same mass on the moon. Mass doesn't change. The amount of atomic material stays the same, okay? All right, so I can use that mass that I've got, both in kilograms and slugs, and that's the mass on the Earth, but it's also the mass on the moon. That's the point I want to make here. Mass is just the amount of atomic material. It doesn't change regardless of where you are. So whatever your mass is on the Earth, you'll have the same mass on the moon. But what will change is your weight, because the gravity on the moon is weaker. It's not as strong as the gravity on Earth. So your weight will decrease on the moon. Okay. Y'all okay with that? I'm doing all right here? All this good stuff written down. Okay. So to find the weight on the moon, I take the mass times the gravity on the moon. Okay. Okay with that? All right, now while I'm thinking about it here, why don't I get you one thing to do for Friday, for starters. Should be problem something or another. Problem how about 112? Let's do that. Okay, so that'll be due Friday. So let's keep that in mind. So 112 is due this Friday. It's problem 112. It's a light fixture. It's on page 1. Okay, so that's in the homework section of your packet, okay? So that's page 112. Everybody okay with that? And then, why don't, okay, in class here, let's have everybody kind of move a little bit. So let's get the, let's see. Why don't we get the civil construction types up here in the upper left? It's got the mechanical manufacturing types over there in the upper right. Chemical, environmental bios back there, and everybody else in the other corner. So why don't we do that real quick? Okay, those of you online, we're working on this thing here. So this is under the homework downloads, Statics Project 1. So it looks like that. So we're just going to have people fill this out. If you can find some people that are in these majors, you know, that would be great. If you have to fill it out yourself, that would be okay too. But I just like you to kind of come up with 4 subdivisions within your major, okay? So the example of a subdivision would be in civil, one of the subdivisions is transportation. That's a subset of civil engineering. So just come up with 4 subdivisions of engineering in your major.